Oh my god, shit!
So what is induction heating? Well, in one line, induction heating can be defined as heating of a material that is usually ferromagnetic by means of inducing currents in the material by surrounding the material in a rapidly changing magnetic field. Now, let's look at how the concept of induction heating came about. As you can see, we have two loops of wires of which currents are traveling in opposite direction. Now, in a high frequency alternating current, the direction of the magnetic field will rapidly oscillate and reverse themselves. Therefore, we can now establish that the direction of the current and the direction of the magnetic field will continuously reverse between these two directions as shown in the loops of wire. Now, let's identify the direction of the magnetic field in each direction of current. Using our right hand grip rule, we can determine that when the current moves from left to right, the magnetic field inside the loop of wire moves into the page. While, on the other hand, in the other loop of wire, when current moves from right to left, we can use the right hand grip rule to determine that the magnetic field inside the loop of wire is moving out of the page. Therefore, the direction of the magnetic field will continuously reverse due to this change in direction of current every few seconds. Now, let's take a look at what would happen if a conductor were to be placed inside these varying magnetic fields. As we know, due to a high frequency alternating current, there would be a high frequency of oscillating magnetic fields. As we know, metals comprise of positively charged ions and negatively charged electrons that are free to move. When they are exposed to varying magnetic fields, a current is induced as an EMF is induced. This causes charges to vibrate and dissipate their electric energy in the form of heat energy. When a current is induced in a conductor due to a presence of a varying magnetic field, the current is known as an eddy current. As we can see here, there is a high frequency alternating current flowing in the coil that is located beneath the surface of the ceramic countertop, and above the ceramic countertop a ferromagnetic iron pan is placed. And due to a changing direction of current, a varying magnetic field is induced that goes through the ferromagnetic iron pan. An eddy current is then induced in the ferromagnetic iron pan, and its electrical energy is converted into heat energy, thereby causing the iron pan to heat up and accumulate heat energy. This also means that only the ferromagnetic iron pan heats up and not the ceramic countertop. The ceramic countertop that the ferromagnetic iron pan is placed on remains cool while only the iron pan heats up. Now, let's take a look at how induction heating is used in welding. A piece of metal that needs to be welded is placed in between a metal coil. And in this metal coil, there is a high frequency alternating current flowing. The various directions due to the alternating current is represented by green and orange arrows. An eddy current is then induced in the conductor, but only in the section of the conductor that is in contact with the varying magnetic field that is induced by the alternating current. The electrical potential energy of the charges is then converted into heat energy, causing the strip of metal to heat up and melt its surface. The piece of metal then gets heated up and is ready to be welded into other metals, or other metals to be welded into this piece of metal.
That an electric current in one piece of wire could induce another current in another wire. But what exactly is induction? Let's go back to the modern age and look closer. It turns out that when electricity flows along a wire, it creates a magnetic field. The lines of this magnetic field curve around the wire in circles like rings around a finger. I'm going to take this loop of wire and stick it inside the magnetic field. The loop contains something called a galvanometer, which is a very sensitive ammeter for measuring tiny currents. Watch what happens. When I insert the loop into this magnetic field, the galvanometer moves. It is detecting a small current. I take the loop out again, and the galvanometer moves again. But if I just hold the loop still like this, there is no current detected at all. My instrument doesn't move. It's only when I move the wire into or out of the field that I get a response. Faraday saw this too, and he realized that an electric current was induced by a changing magnetic flux. Flux is given by the strength of the magnetic field multiplied by the area of the loop moving through it. In order to get a current inside the loop, the magnetic flux must change. This only happens when I stick the loop into the field or take it out. When it's completely inside the magnetic field or completely outside it, the flux does not change. Induction, ladies and gentlemen, the manipulation of electricity through a changing magnetic flux. Today we call it Faraday's law.
What is Faraday's law? Well, it's basically an EMF which is induced in a circuit if the flux linkage through the circuit changes. It is denoted by a formula which is EMF equals to negative N change in flux over change in time. The N represents the number of loops. The negative sign there is basically to denote Lenz's law, which is just to prove direction.
So Lenz's law states that the direction of the current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field. So in the diagram, a magnet bar is shown moving downwards towards the coil. So when the magnet bar moves through a coil, an opposed magnetic field is produced. Figure 1 shows that when the magnet bar moves downwards, an opposing magnetic field is produced. In this case, a current that moves anti-clockwise produced, which can be determined through right-hand grip rule. Similarly, in figure 2, when the magnet bar moves upwards, a clockwise current is produced. The following video shows that a magnet is dropped through a copper pipe is falling much slower compared to release in the air.
Magnets to the copper, doesn't work. But if I drop them through, watch what happens. 3, 2, 1. They fall really slowly. Here we go, one more time. 3, 2, 1. Something's slowing them down. You can hear that they are hitting the sides of the copper. 3, 2, 1. Look at that. Let's try one more time. 3, 2, 1. And they hit. Much, much slower.
So when the pipe moves across the magnetic flux density at each point along the copper changes, that creates an electric current. And by Lenz's law, that electric current will produce a magnetic field that opposes to the magnetic field of these magnets, causing the hanging magnets to move. This is why the earlier video that shows that the magnet falls through the copper pipe slowly is because the magnetic field they induce in the copper pipe is counter to their magnetic field. This can also be described through conservation of energy. Energy to produce electric current in the pipe and the magnetic field comes from the falling magnets. Thus, magnets fall more slowly as that energy is being converted into electric current. And that current created by a moving magnetic field is called eddy current.
So now, let's look at the advantages of induction heating. Firstly, it only requires a short amount of time to heat up metal parts due to a high heating speed. Cost of operation of induction heating is lower than other methods of heating, as induction heating is highly efficient. More products in the form of heat energy can be produced by reducing heat energy loss to the surrounding via radiation, conduction, and convection. And also, during induction welding, surfaces that oxidize and decarbonize will be kept at low arbitrary levels. This keeps the structural integrity of the workpiece intact. Besides that, deformed workpieces can also be straightened by using induction heating. Workpieces that straighten through induction heating will be hardened, which causes it to have anti-fatigue breaking ability. On the other hand, induction heating devices is more expensive due to its complex design, which requires high capacity investment on an industrial scale. Secondly, only specific metals can be induced. For example, high purity iron materials can be heated by using electromagnetic induction, whereas high carbon composition steels cannot be heated by using electromagnetic induction. Induction heating cannot be easily manipulated to suit the needs of the consumer, therefore causing it to have a poor adaptability. Similarly, induction heating cannot use for complex design. Complex metal workpieces that use induction heating is difficult to guarantee its quality. In conclusion, there are clearly more advantages compared to disadvantages, and this is the main reason why induction heating devices are more popular globally. However, there are also several ways to increase its efficiency. The first one is to increase the magnetic permeability. This can be achieved by increasing the current frequency and also decreasing the magnetic field. Next is to increase the number of wires in a bundle and make it possible to use a lower frequency at the same efficiency. Lastly, We can also improve it by using linear conduction coil, which can maintain the minimum gap upon heating of wires, having different diameters and increase the efficiency up to 55%.